This lecture is given by Professor Remko Uijlenhoet from Wageningen University and Research. Professor Uijlenhoet is a well-known hydrologist. He is a professor of hydrology and quantitative water management in Wageningen in the Department of Environmental Sciences. He is known for quite a number of projects in the area of hydrology and related activities. He is a member of various scientific committees and member of editorial boards of journals. So Professor Uijlenhoet, you're welcome to make your presentation. So again, it's 45 minutes for presentation and 15 minutes for questions. Thank you very much for agreeing to give this lecture. Floor is yours.
Yeah, thank you very much, Professor Solomatine and Professor Gelfand for the invitation to be with you as a lecturer today. And I would also like to thank the previous speakers, Professors Kunzewicz and Kutsuyanis yesterday afternoon, Dutch time that is, and earlier today, Professor Chu from China. Really happy to be with you today. I'm going to start my presentation. One moment, please. There it is. And it should be on full screen now. Is that correct, Dimitris?
Yes, it's all going
great.
well.
Okay, thank you very much. So really happy to be here, and the topic of my presentation today will be quantitative precipitation estimation and quantitative precipitation forecasting for hydrological applications. Indeed, my name is Remko Uijlenhoet. I'm with the Hydrology and Quantitative Water Management Group at Wageningen University and Research in the Netherlands. Really happy to be here. I'm going to talk today about two subjects. We have 45 minutes in total, so I have to limit the number of subjects I will be dealing with. The two main subjects, as indicated by the title of my presentation, are quantitative precipitation estimation, QPE, and quantitative precipitation forecasting, QPF. Regarding QPE, I'm going to be dealing with a number of aspects. First of all, I'm going to give you a rationale, basically a motivation for this work. Then I'm going to focus on relevant spatial and temporal scales from a hydrological perspective. Subsequently, I'm going to focus on two particular ground-based sensors used for quantitative precipitation estimation, namely rain gauges and weather radar. Further on, I'm going to touch upon new possibilities opened up by opportunistic sensing techniques. And finally, I'm going to devote about the last 10 minutes or so of this lecture to quantitative precipitation forecasting. And I'm going to particularly pay attention to radar rainfall nowcasting, which is of great relevance for catchment hydrology and water management. And anytime I will change topics or change gears, I will show you this particular slide. So, you know, when you see this slide, that I'm going to change from one aspect of the topic of quantitative precipitation estimation and forecasting to another. So this then basically starts the first part of the presentation. Let's start with the hydrological cycle as it was introduced yesterday already by Professor Kunzewicz. And it's obvious that precipitation plays a very important role in that hydrological cycle, as it represents the main source of water for all terrestrial hydrological processes. And therefore, precipitation estimation and precipitation forecasting is of the utmost importance for hydrologists, both from a scientific perspective as well as from a water management perspective. So the next 3/4 of an hour will be focusing on one particular flux within the hydrological cycle only, namely precipitation. And as you all know, precipitation is extremely variable on all scales. The top graph on this slide shows a yearly rainfall climatology, an average yearly rainfall map deduced from satellite imagery, in this case the tropical rainfall measuring mission, clearly showing you that even on a yearly average scale, there is strong variability of rainfall at global scales, as we all know very well, an important aspect of our climate system. But if we start to zoom in, both spatially as well as temporally, we come up with the graph on the lower left-hand side, which is a weather radar image of the Netherlands and vicinity. And again, we see a precipitation map with the lighter colors indicating higher intensities and the darker lower intensities. And again, you see that rainfall on the scale of a few hundreds of kilometers is again highly variable. And if we zoom in even further, we come to the image on the lower right-hand side, which is a high-resolution radar image of a radar that used to be on the Delft campus some time ago. And this shows you image of distances up to 15 kilometers from the radar. So really short distances, but again, very high and strong variability at short spatial and temporal scale. So we can conclude from this, as we all know very well, that precipitation is an important flux, really important from a hydrological perspective, but that it's highly variable in space and time over all scales. Hence, its relevance to understand the backgrounds of this variability and also our motivation as hydrologists to measure it. Now, not only is rainfall very highly variable in the horizontal, it is also highly variable in the vertical, as is shown by this vertical cross-section through a rainfall event. In this case, a rainfall event that occurred in the south of France, a stratiform event, which can be clearly seen by the bright band indicating melting snow particles. But what you can very clearly see from this image is that the horizontal variability of rainfall is to some extent a representation or a consequence of processes occurring aloft. And those processes will not be the main topic of the presentation here today, because the topic here is not meteorology but hydrology, but it's important to keep that in mind. Now, of course, as hydrologists, we typically investigate hydrological processes at a particular spatial scale, namely the spatial scale of river catchments. And what you can see here is a map of Europe as it could be drawn by a hydrologist rather than a politician, showing you some of the major gauged river basins in Europe. And the red basin in this particular case is the Meuse basin, one of the tributaries that is important for the Netherlands. And also I indicated the locations of a number of research catchments that are important for our research as well as research of other hydrology groups across Europe. So a typical spatial scale at which we investigate hydrological processes is the river catchment. And this digital elevation model shows you a close-up of one such river catchment, namely the Ourthe Basin in Belgium, in the Ardennes area just south of the Netherlands, which is a 1,600 square kilometer catchment, which has been quite heavily investigated over the past years from a hydrological and hydrometeorological perspective. But obviously, what can be seen here is that within a catchment like this, there is a rich variety in terms of not only altitudes, but also in terms of landscapes, vegetation, and what's more. And we try to capture that variation in space within our catchment in typical catchment hydrological models, which we employ together with quantitative precipitation estimates and quantitative precipitation forecasts to produce predictions of runoff of catchments like this, as is shown in the middle on the right-hand side of this graph. The endeavor to develop hydrological understanding of the functioning of river basins and translating that understanding into hydrological models has been a favorite pastime of hydrologists over the past decades, if not centuries. Ultimately, of course, what we would like to do once we have gained hydrologic understanding is to use that understanding to understand and explain the phenomena that we observe in river catchments. And in this case, I'm showing you one particular heavy rainfall event that hit our national hydrological observatory in the east of the Netherlands, a very small 6.5 square kilometer research basin, which towards the end of August 2010 was hit by about 160 millimeters of precipitation, which for the Netherlands is really heavy. And that produced the highest discharge peak ever in this particular catchment. And as research hydrologists, we were really happy that our colleagues in the past designed the flume such that it was able to relatively accurately measure that peak discharge. We would have never thought that that would happen, but it actually did in August 2010. Of course, the models that we're developing can be used not only to help us in gaining scientific understanding, but also in order to be used in water management. For instance, to provide warnings for natural hazards such as flash floods, where clearly in this case people were warned too late to leave their houses without casualties, luckily, in the south of the Netherlands. And an important other application, of course, of our hydrological knowledge, apart from real-time water management applications, considers applications in hydrologic design. In this case, you see the example of a sewer system that clearly was not able to withstand the enormous amounts of rain that you see on the left-hand side. So those are a few types of applications: hydrological process understanding on the one hand, real-time flood forecasting applications, as well as hydrologic design, which are important to us hydrologists and for which quantitative precipitation information, both currently and in the near future, are of the utmost importance. Hence the focus of this presentation on QPE and QPF. And that brings me to the second part of my presentation. We're going to focus a bit more on the relevant space and time scales, because they will reveal to us to what extent we need a particular spatial or temporal resolution when it comes to our precipitation estimates. Now, in this case, in this example on this slide, you see two graphs from a paper by Jim Kirchner from 2009, where he shows rainfall runoff, rainfall discharge, I should say, relations for two particular catchments in the well-known Plinlimmon area. And what you can very clearly see is that typical catchments are actually low-pass filters transforming the highly erratic, high-frequency variations that are apparent in the rainfall signal, in gray in this case, into lower frequency signal, which is represented by the discharge, the bold black line in this case. And so these low-pass filters have a particular memory, and that memory can be a catchment response time, and it's important for us to understand the variation of that catchment response time depending on catchment properties, as well as its dynamics, for instance, during seasons. because it's that catchment response time that actually dictates at what temporal resolution we need to measure rainfall. In this particular case, you can very clearly see that the time steps that are employed to measure rainfall at the narrow vertical gray bars, those time steps are much smaller than the typical length of one hydrograph. And that, of course, is very important if we want to be able to resolve the full dynamics of a rainfall runoff process. So to that extent, the response time of a catchment gives us a upper limit as to how coarse we can measure rainfall in time. And ideally, obviously, we should be at a fraction of that if we want to really understand the dynamics of river catchments. So let's take a closer look at those catchment response times and how they vary with catchment property, and in this case, focusing on one particular catchment property, namely catchment area. So here you see on the horizontal axis the surface area, in this case of a number of urban catchments in the south of France and in a few other places. And on the vertical axis, you see the lag time. And the lag time was determined, as shown in the lower right-hand side, by simply taking the difference between the center of gravity of the rainfall event and the center of gravity, or center of mass, would be better, of the discharge event. And if you plot that lag time for a whole number of events, you average it for a given catchment, and you plot it versus catchment area, obviously you see that the lag time on average tends to increase with the surface area of the catchment, roughly as indicated in this graph according to a power law. What is important here is that given the surface area of a catchment, we are able to determine a lag time using this average regression line. And that lag time, as I stated before, gives us an upper limit as to the temporal resolution with which we should be measuring our precipitation. And ideally, actually, that should be measured at a fraction of that lag time, let's say a tenth or so, as a rule of thumb. This shows you a similar graph, but now over a much broader range of scales. So again, on the horizontal axis, watershed area, and on the vertical axis, the response time. The catchments that we just studied are on the lower left-hand side of this image. But again, what you can see if you go to larger catchments, as indicated by the black dots for, in this case, the Rhone River in France and a number of large tributaries, you see that for larger catchments, on average, response times tend to increase. Now, it's important, as I just indicated, because that gives us a clue as to the temporal resolution with which we need to mimic the rainfall runoff process. But it's also important for us to understand which types of precipitation systems are important in causing actually discharge events for this type of these types of catchments. So what you can see over here is a bold black straight line, which basically indicates the typical lifetime of meteorological systems as a function of their surface area. And we move on the lower left-hand side of the screen from thunderstorms via mesoscale convective systems to frontal and stratiform systems. So what this graph shows you is that for the small, rapidly responding catchments, the resonance, if you will, with short duration, heavy rainfall events induced by thunderstorms are the most relevant type of meteorological event producing peak discharges. Whereas for medium-sized catchments, typical mesoscale convective systems play an important role. And for the very large catchments, actually, frontal systems play a decisive role when it comes to producing the peak discharges. So Not only does a graph like this give us a clue as to typical time steps that we need in our simulation of rainfall runoff processes, but it also gives us a clue as to what types of weather systems are relevant in producing the highest discharge peaks. Now, once we know at which time step we need to measure precipitation and we need to model the rainfall runoff transformation process, we also have an idea about the spatial resolution with which we need to measure rainfall. And that is because the spatial variability of rainfall is very closely related to the temporal variability of rainfall. Now, that is clearly shown in this particular graph, which I took from a paper by Villarini et al. 2008. So what you can see here are basically correlograms deduced from rain gauge time series, in this case from a rain gauge network in the United Kingdom. And what is shown here are different correlograms going from high resolution rainfall on the upper left-hand side. So these are 1 minute time steps. Subsequently, these are aggregated to 5-minute time steps, 15-minute time steps, and so forth, to daily time steps on the lower right-hand side. And what you can very clearly see from this graph is that correlations obviously increase once we start to aggregate temporally. So once we start to aggregate rainfall temporally, the spatial scales that are so important for hydrological applications also become coarser. And through graphs like these, we can understand how the required time step of our, let's say, simulations, rainfall runoff simulations, are so closely related to the relevant spatial scales at which we should be measuring rainfall. And from graphs like these, hence, we can derive typical densities of rain gauge networks that we need in order to understand the dynamics of the rainfall runoff transformation in the catchment that we're studying. And for example, if we have a catchment that has a very short response time, such as the urban catchments that we saw earlier, we might need to measure rainfall and simulate the rainfall runoff transformation at a 1 minute or a 5-minute time step. Well, if we need to model the rainfall runoff process at time steps of a few minutes, that means that we need to have a rain gauge network where gauges are very close together, because decorrelation distances of rainfall at the 1 or 5-minute time step are very short. Whereas if we have a much slower responding catchment, for instance, because it is much larger, where, for instance, daily rainfall information would be enough to accurately mimic the rainfall runoff transformation, then obviously we can do with much coarser rain gauge networks, because the rainfall decorrelation distance at the daily timescale is much longer than it is at shorter timescales, as shown by the graph on the lower right-hand side. So obviously these properties of precipitation depend on the season, depend on the particular climatic setting where the catchment of interest is located, but it is a general property of rainfall that once you start to aggregate it in time, that the decorrelation distance also becomes longer. And that is summarized in a graph like this, where we plot as a function of time step on the horizontal axis, the decorrelation distance on the vertical axis. And again, you see power law relationships appearing. I also quoted a number of such relations from the literature, indicating that if you go to aggregate precipitation from minutes to hours to days, the decorrelation distance also becomes longer. And that means that for catchments that are more rapidly responding, we need denser rain gauge networks, whereas for catchments that are slower responding, we only need coarser rain gauge networks. And the details, obviously, of this relationship, again, depend on the particular climate or the season that is relevant. But this shows you the general behavior of these relationships. Which brings me to the next aspect that I'm going to talk about, and that is concerning rainfall measurement. Now, we are all familiar, I guess, with rain gauges and rain gauge networks, but over the past years and decades, weather radars have also become standard tools among hydrologists to measure precipitation. And obviously, one advantage of a weather radar is that it is able to provide that high spatial and temporal resolution that is needed to mimic the behavior of even small, rapidly responding catchments. But that comes at a price, because weather radars do not measure rainfall directly. They are a remote sensing technique, and hence there are all kinds of errors that affect the quality of quantitative precipitation estimates from weather radars, and some of them are indicated on this particular slide. Now, the approach that we have taken in our research over the past 10, 15 years is not to correct for all these different error sources by simply adjusting using data from rain gauge networks. The approach that we have taken over the years is to take the physical causes of error in rainfall estimates from weather radar into account before comparing them and ultimately maybe correcting them using rain gauges. And one example is given over here, that is attenuation of the radar signal caused simply by rainfall on the radome, which is the cover over the radar antenna. And this shows you a time series of reflections from basically buildings, which are normally a nuisance in weather radar images. But in this case, what you can very clearly see is that during the 26th of August, the reflection from those buildings suddenly decreased significantly. And that was not caused by changes in these buildings. That was caused by the fact that rainfall was falling on the radome covering the radar antenna, causing attenuation of the radar signal at the site of the radar itself. And obviously, once you see this, this is something that you can correct for, and that is something that we operationally apply. Another type of error from the perspective of precipitation estimation in weather radar imagery is the so-called vertical profile of refractivity. Already earlier on in this presentation, I indicated that rainfall is highly variable, not only in the horizontal, but also in the vertical. And knowing that typical weather radar images do not pertain to rainfall at the ground, but to rainfall, for instance, at 1,500 meters above the ground, you can understand that it's important to make the appropriate translation of rainfall aloft to rainfall at the ground. And we do that by means of a vertical profile of reflectivity correction. It would take too long to go into details at this particular moment, but it just is shown here to indicate to you the importance of taking those physical error sources into account before confronting radar data with rain gauge data. And that is what we have done over here. So what you see here are scatter plots of rain gauge measurements on the horizontal axis versus radar measurements on the vertical axis. And those are radar estimates of rainfall at the ground before using rain gauges to adjust them. So this is radar standalone, but after taking into account a number of error sources that we know have played a role in these images. And what you can very clearly see is that you can already obtain pretty high correlations and relatively limited biases without adjusting radar rainfall images using rain gauges. On the left-hand side, you see hourly data for 3 days, 42 rain gauges over the Uijlenhoet catchment in Belgium that I have shown you before. And on the right-hand side, you see the same, but now aggregated over the entire event. Obviously, we can do the same thing, not just for an event of a few days, but for an entire season, in this case, the winter season. Obviously, there is a significant amount of variability, of scatter, comparing rain gauge and radar estimates. But what you can very clearly see here is that if you take into account systematically physical causes of error in the radar images, you can already obtain high correlations and low biases compared to rain gauges, even before using rain gauges for adjustment. And only after taking these physical error sources into account do we start using gauges for adjustment. And this is then finally what you can obtain if you apply this to catchment average discharge, in this case over a 1600 square kilometer catchment, the one I showed you before, again indicating that careful accounting for error sources in the radar images gives reasonable correlations and low biases with respect to gauges before correcting them. And this shows you exactly the same data, but now spread out over the entire winter season. On the horizontal axis time, and on the vertical axis the ratio between radar and gauge, where obviously one would be the ideal, and this is per day for the entire catchment, before again taking rain gauges into account to adjust the radar images. And of course this reflects both uncertainties remaining in the radar estimates of precipitation, as well as remaining uncertainties in the gauge estimates of catchment average rainfall. But overall, you can see that the bias is relatively small, which is important for hydrological applications. And a hydrological application is demonstrated here, where both the radar images before adjustment by gauges and the gauge estimates are used as input for a rainfall runoff model with interesting results. Okay, that brings us to the next topic of my presentation, and that is the potential of novel measurement techniques. Now, we have seen radar imagery, and radars can be both mounted at the ground as well as on board of satellites, as we have seen before. Of course, the disadvantage of satellite precipitation estimates is that they are very indirect estimates, and hence we need so-called ground truthing in order to obtain quantitative precipitation estimates for hydrological applications. We have seen weather radars, which can be really useful instruments for hydrological applications. But of course, if you look at the global distribution of weather radars, you can see that they are dense in terms of their networks in only certain parts of the world, whereas in other parts of the world, the density of networks from weather radars is really low. And that shows that there is enormous potential for other techniques for measuring rainfall. Obviously, we have our rain gauge networks, which have been so useful to us hydrologists for many decades. But what you see here is that, particularly on the right-hand side, that actually the densities of reporting rain gauges are actually declining worldwide. So the number of gauges from which information is available to end users, both online and offline, is declining. And that, of course, is a very worrying evolution. That is not just worrying in itself, but also worrying because we need gauges to better quantify errors and uncertainties in both weather radar estimates as well as in satellite estimates of rainfall. Now, at the same time, what we're also witnessing is a revolution when it comes to the usage of mobile cellular devices. This shows you the number of devices used worldwide on the vertical axis versus time. And here you see that already in 2013, there were as many cellular devices as there were people on the planet. Obviously, with great variations among different continents, but nevertheless. And that has basically stimulated us to think of the use of infrastructure developed for mobile telecommunications for the purpose of rainfall measurement. And we call that opportunistic sensing, basically indicating that we are using infrastructure opportunistically, infrastructure that was not built or designed for measuring rainfall, as opposed to dedicated infrastructure such as rain gauges here on the left-hand side of the screen, or weather radars on the right-hand side of the screen, which were designed and built to measure rainfall. Now, you are all very familiar with the commercial microwave links, of which we see the antennas everywhere nowadays. It's obvious that when it rains, radio signals transmitted from one antenna to another will be attenuated due to absorption and scattering of the radio signals by the raindrops. And our idea is to use this attenuation to estimate rainfall as a supplement to rain gauges, weather radar, and satellite imagery. And that indeed there is enormous potential for this technique is shown in particular by the graph on the upper right-hand side, which is the exponent of the theoretical power law relationship between rainfall rate, capital R, and K, which is the specific attenuation. What you can see is that the exponent of that power law relationship becomes about 1 for radio frequencies of the order of 30 gigahertz. So that indicates that for radio signals of the order of 30 gigahertz, the attenuation suffered by a radio signal propagating through rainfall is proportional to the rainfall rate. And that suggests that microwave links operating at that frequency can actually be used as path average rain gauges. Now, much to our surprise, the typical frequency employed by mobile network operators in their cellular communication networks is actually about 30 gigahertz. So that suggests that microwave links from cellular communication networks can be employed as path average rain gauges. And that is shown for one particular microwave link in the city center of Amsterdam on this particular slide, where you see on the upper left-hand side that the received signal level decreases whenever it is raining. Raining is indicated by the gray line, basically a radar estimate of rainfall along that line. And using that theoretical relationship that I showed you on the previous slide, we can actually transform the attenuation suffered by the microwave signal, which is stored operationally by mobile network operators to monitor the quality of their networks. We can transform that to rainfall rates, which is shown here on the lower left-hand side, and ultimately to rainfall accumulations. Now, obviously, if we can do that for one particular microwave link, we can do so for many microwave links, as indicated here. Here we used on the left-hand side about 2,500 commercial microwave links from one mobile network operator in the Netherlands. We estimated path average rainfall per link, and we interpolated between the links using a geostatistical interpolation method. And on the right-hand side, you see the best available rainfall product from our National Weather Service using 2 weather radars, 35 automatic rain gauges, and about 350 manual rain gauges. And what you can very clearly see here is the enormous potential of microwave links for estimating rainfall, which basically is an indication of the potential of opportunistic sensing techniques for basically complementing dedicated sensing techniques such as radar and gauges. In particular, in those areas of the world, obviously, where there are no weather radars, very few rain gauges, but where people are using their cellular devices. And location that can be mentioned explicitly there is the African continent, where we've given a summer school a number of years ago on this topic. And on the right-hand side, you see information obtained from one mobile network operator over the capital of Nigeria, Lagos, in this particular case, where there are few rain gauges and weather radars, but where the density of the microwave link network is very high, showing you the enormous potential that can be obtained in developing countries where dedicated sensing networks are very sparse, but there is enormous potential for opportunistic sensing. Now, this slide shows you a topic that I'm not going to deal with in view of time in detail here, namely the potential of using smartphones for temperature measurements in cities. But this slide is again relevant for rainfall estimation. This shows you the potential of personal weather stations. More and more people these days buy personal weather stations to be installed in their backyards or on the roofs of their houses. And one of our research colleagues has demonstrated that you can use these personal weather stations after careful quality control to estimate rainfall in space and time. And here you see a comparison between, on the right-hand side, those personal weather stations, of which the data are freely available on the internet, compared to, again, a product based on radar and gauges on the left-hand side. So this all shows us that there is enormous potential for opportunistic sensing techniques, commercial microwave links, personal weather stations, to complement dedicated sensor networks, both from rain gauges and from weather radar. And that will bring me to the last part of my presentation, but I see Professor Solomatina already being present here. Do you still give me 2 or 3 minutes to wrap up my presentation?
Professor Uijlenhoet. Yes, sure.
Okay, thank you very much. Because the last part of my presentation deals with short-term forecasting, namely nowcasting of rainfall. And you probably know this very well from apps that we all carry on our smartphones these days. Of course, the principle is very simple. You take a number of radar images from the recent past and you extrapolate them into the future. But obviously, the way in which you do that tells you a lot about the quality of the forecasts that can be obtained. And high quality is definitely needed for hydrological applications. So basically what you do is you take a couple of radar images from the recent past, and you basically deduce a motion field from those radar images, and you extrapolate that using that motion field, the observed rainfall field into the near future. Now, you can do that both deterministically and stochastically by perturbing both the rainfall field as well as the motion field. And what I'm going to show you in the final couple of slides is basically how this approach of what is called nowcasting could basically bridge the gap between simple Eulerian or Lagrangian persistence and numerical weather prediction models, as is indicated on this particular graph. So we've basically taken a number of such nowcasting techniques, which are indicated here in the table, and applied them to an enormous database of over 10 years of radar data and apply them for rainfall estimation over a number of catchments in the Netherlands, from only a few square kilometers to about 1,000 square kilometers. Overall, we've done this for over 1,500 rainfall events for different seasons and different durations. And this shows you an example of one such application from one particular technique. And we have evaluated the performance of those nowcasting techniques with respect to measured rainfall by weather radar. And this shows you an example. On the top row, you see measurements of a radar for future moments. And on the lower panels, you see forecasted rainfall using the various techniques that I presented. Now, we've calculated the statistics over many events, as I said, more than 1,500 events of various durations. And our results clearly show that in particularly for the longer duration events, stratiform precipitation, significant skillful lead times of the order of 2 hours, 160 minutes in this case, can be obtained by the best of such nowcasting techniques. So this shows you the potential of nowcasting to fill the gap between Lagrangian and Eulerian persistence on the one hand, and numerical weather prediction and meteorological models on the other hand. I'm coming to the end of my presentation now. This shows you that, of course, the quality of those nowcasts depends very much on the season. In the Netherlands, typically, we have stratiform precipitation in the winter, which is easier to predict than the more thunderstorm-like convective precipitation in the summer, as is clearly indicated in this particular graph. I could also indicate to you that catchments that are more downstream with respect to the prevailing wind direction obviously have longer lead times corresponding to them, but that would take too long to discuss that in detail over here. And obviously, the larger the catchment, the longer the skillful lead time, as can be imagined. For a very small catchment, it is very difficult to obtain a reasonable rainfall nowcasts until long lead times. That is, of course, basic hydrological knowledge. So we've investigated the performance of these algorithms as a function of event type and duration, as a function of season and location and catchment size. So that brings me to the final slide of my presentation, summarizing our findings. You need to carefully process radar imagery before you apply them in hydrological models and before you combine them with rain gauge information. There is enormous potential in opportunistic rainfall measurement techniques such as microwave links and personal weather stations. And finally, there is great potential from a hydrological perspective in statistical nowcasting techniques, filling the gap between, on the one hand, persistence, and on the other hand, numerical weather prediction. And with that, I would like to thank our sponsors and PhD students and thank the audience for their attention. Thank you very much.
Thank you very much, Professor Uijlenhoet. Really very interesting talk on new technologies and opportunistic measurements and citizen science. I would like now to move to questions. I'm sure there are several questions, quite many questions, so we have to choose which ones we pose if we have time. Pelageya Belekova from Russia asks, what temporal resolution of precipitation could be optimal for flash flood simulations? And the question is about mountainous rivers with basin area of 50 to 100 kilometers square.
Yeah, that is an excellent question. Thank you very much. Of course, that depends very much on the typical response times of the catchments that we are talking about. But if you will take a look at the graphs that I showed earlier on in the presentation, you would be able to see that I would guess for flash floods in catchments of the order of a few 10 square kilometers, you would need rainfall information at, let's say, the 5-minute or so time scale, 10-minute time scale, and 1 square kilometer resolution, which is the typical time scale that can nowadays be obtained from weather radar imagery. It depends very much, I would say, whether those catchments are in rural or in urban areas, and that was not clear from the question.
Yeah, that was more about the system which is being developed for southern Russia for flood forecasting and flood warning, and this is rural area mainly. But I'm sure if Dr. Belikov would have a question about this, she could maybe contact you later.
Definitely.
About this detail.
Definitely.
Yeah, thank you. A question from Boris Gartsman. What kind of correlation is used for precipitation observations of daily and shorter time step? A simple correlation coefficient looks inappropriate for this.
Yeah, that is definitely a correct remark. So what is often used in these studies is the simple Pearson correlation. Which obviously, if you apply a Pearson correlation to a highly skewed phenomenon such as precipitation, particularly at shorter durations, you may have biased estimates of the correlation coefficient. That is well known. But the figures I showed earlier from the paper indeed employ that Pearson correlation coefficient to rainfall accumulations all the way down to intervals of the order of 1 minute. So I fully agree with you that you may want to transform the rainfall field before computing correlation coefficients to obtain a more, let's say, normally distributed random variable. But obviously that would affect the correlation estimate. In this case, I quoted numbers from the literature, and as far as I know, most of the researchers reporting those correlations simply calculated Pearson correlation coefficients.
Thank you very much. Another question, why radar applications to hydrological models showed lower discharge output in comparison to rain gauge application? How many rain gauges were used? You showed the picture with flood simulation.
Yeah, that is a very good question. That is actually a question I would have expected from the students in our class too. So thank you very much for that. Actually, if you take a close look at that particular graph, you would be able to see that the radar underestimates rainfall in the days preceding that enormous flood peak. And that is because precipitation during those days did not fall as rainfall, but as actually snow. And weather radar is, well, not the ideal instrument to estimate snowfall quantitatively. So basically what happened is that in the simulation, the rainfall or the precipitation was not observed by the radar, and the model actually, so to speak, ran dry, and therefore the flood peak following that snowfall period was underestimated compared to simulations based on the rain gauges. Yeah, so that had nothing to do with the fact that radar was not operating correctly during the flood peak, but that had to do with the radar basically not being able to measure solid precipitation.
Thank you very much. And Professor Uijlenhoet, maybe you could stop sharing presentation. You are still doing this, if I understand correctly. Then we could see you in full screen. Thank you. Yes, excellent. And of course, you can get back to it if you need to show some slides. All right. Next question comes, let me, my page, yes, from Nikolai Yasinski. Professor Uijlenhoet, please, could you make it more clear what were correlations between gauges and radars before VPR correction? So before the vertical profile of reflectivity correction.
And okay, yes, so I have not included those in my presentation, but you can look them up in the paper that I refer to in the presentation. And what you can find in that particular paper is that the correlations increased somewhat, but not that much with respect to before the correction. But in particular, the bias was reduced with respect to the radar gauge comparison before the correction. So the correction for the vertical profile of refractivity is in particular important to reduce the bias, not so much to reduce the scatter, so to speak.
Right. Thank you very much. And another question from Nikolai Yasinski refers to using artificial intelligence. So question is it effective to use artificial intelligence in order to make VPR correction? Or is it better to use it directly for radar gauges data without any correction?
Yeah, thank you very much. That is indeed a very interesting technique that is becoming more and more popular these days. Machine learning, for instance. And indeed, as Professor Solomatina is very well aware of, there is enormous potential for these techniques in hydrological applications, also in quantitative precipitation estimation using radar, but also, for instance, in quantitative precipitation forecasting. So definitely there's potential. We have not investigated the potential in radar rainfall estimation, but we have currently started investigating the potential of machine learning techniques in short-term rainfall prediction to see whether or not these techniques would outperform the statistical nowcasting techniques that I presented in the last part of my lecture. Yeah, thank you very much for that question. Really interesting.
Thank you very much, Professor Uijlenhoet. Chris Marsh from Canada is asking, I'm wondering if the microwave link approach has been investigated for solid phase precipitation, for example, snowfall.
Yeah, thank you very much for that question. Basically the same as for radar. Radio waves at these frequencies of the order of several to tens of gigahertz are in particular sensitive to liquid rainfall, liquid precipitation, much less to solid precipitation. That has to do with the electromagnetic properties of snow and ice with respect to those of water. So typically you see much less backscatter from the radar and much less attenuation in case of the microwave links from snow and hail than you would see from rainfall. So I would say definitely very interesting to investigate that further, but it's much more difficult to estimate snow and hail using radar or microwave links than to estimate liquid precipitation, namely rainfall. Colleagues of ours in Switzerland have tried to do so, and I can see the potential for that technique also in other high latitude and high altitude environments.
Thank you very much. Another question is from Russia, from Viktor Lomov. Your research is focused on observations methods mostly, but what is your opinion about using reanalysis data for the same goals of precipitation estimation?
Yeah, definitely reanalysis data serve an important goal, namely offline studies. Reanalysis data cannot be employed in, let's say, real-time applications where you need to know here and now the amount of precipitation. So we need measurements by gauges, by radar, by satellites, or by opportunistic sensors in order to have an idea of the state of the atmosphere at this particular moment. But obviously, a reanalysis does not exist without measurements. A reanalysis is a, let's say, optimal combination of measurements and model output in the recent past. So basically the perfect reconstruction of what the past precipitation has looked like. So for many offline applications, many offline studies in hydrology, reanalyses are definitely important, and we are also using them in our research. Yes.
Thank you very much. Now, question again from Mark Ehrlich from France. What are the methods for validation of data collected through Citizen Network? Do you use a subset of verified and certified observers?
Yeah, thank you very much for that question. So basically what we have developed is a automatic quality control system to apply to the data from the personal weather stations. Obviously, citizens do not install rain gauges according to requirements as for instance put forward by the World Meteorological Organization. So many people actually install rain gauges in inappropriate locations, but you can actually filter those gauges out using let's say statistical techniques, and that is what we have applied to a very large data set, personal weather station information for the Netherlands. And this algorithm, which actually is available as open source code, is now also being employed by other countries, notably Belgium and Norway, to apply to personal weather station information from their respective countries. So indeed, careful quality control is very important. I fully agree.
Thank you very much. One more question from Mark. How radar-based forecasts would be affected by the effects of mountainous area?
Yeah, that is a very good point. Obviously, the potential of nowcasting techniques in a relatively flat country such as the Netherlands probably provide a best case estimate of the potential of such techniques. I fully agree that for applications in mountainous regions, probably the use of numerical weather prediction models would give much needed added performance. Still, I think that for a very short-term nowcasts over urban areas, notably also in mountainous regions, nowcasting techniques such as the ones presented in my lecture could be useful for short-term weather forecasting and also for short-term warnings.
Thank you. Of course, this question comes from France because Mark lives in the mountainous area, and you, Remko, is a very flat area. Sure.
I have lived in France in the mountains though for several years, so I know the challenges of precipitation estimation and forecasting in those areas too. Thank you.
Yes. Now, last maybe question from Alex Room. To what degree machine learning is incorporated in mobile network data analysis and verification?
Yeah, thank you very much again for that question, pointing to machine learning. At this moment, we have not yet applied machine learning techniques. We basically apply relatively standard statistical techniques to identify outliers and remove them per microwave link, and we interpolate between the microwave links using standard geostatistical techniques. So in that sense, at this moment, we are not yet applying machine learning techniques to those types of data, but we publish our code open source, so it's for anybody to use and also to add. And we also publish many of the microwave link data sets that we used also open source. So if people want to play with those data and with the code and, for instance, try the potential of machine learning to those data, then I definitely invite them to do so, and would also be happy to lend a hand if needed.
That's very interesting. So, by the way, maybe we could have a MSc student doing this in Delft or maybe in Moscow. Right. Okay. Well, I see Alexander Gelfand perhaps also wants to ask a question, or you think we exhausted our time?
Yes, its time is over, but thank you very much for a very interesting presentation, not only for students, for me also. So thank you very much.
Okay, well, thank you very much, Professor Gelfand. Thank you very much, Professor Solomatine. And yeah, thank you very much to the audience for listening and also for the stimulating questions. And indeed, if you need more information about the papers or our work, or you would like to collaborate, just send me an email.
Right. Thank you very much, Professor Uijlenhoet. So as you know, we have quite many registrations for this school, 460, I think, around. Of course, not everybody is attending every lecture, but we will be continuing. So thank you very much again. Audience is applauding. And we have a 8-minute break before the lecture of Professor Bardossi, who I see already appeared in Zoom. Thank you very much.